Thank you very much, John. I would like to thank Mushin and John and their entire team for organizing this quantum gravity school. It's a pleasure and an honor to speak here. I decided to make slides and do not write on my iPad live because usually we give these lectures on 6 blackboards. You don't need to take notes. They will be provided, so you can just listen. And as John said, I'm very happy to take any questions that you have while we go through the lecture. So my part is to give you an introduction to the canonical formulation of loop quantum gravity. And we have 5 lectures, and I will cover 5 topics. Maybe they fit one each lecture, but maybe I will be a bit flexible if one topic is covered a little bit longer than the others. What I would like to tell you in these 5 lectures is a first brief motivation. Why do we think it's interesting to work on quantum gravity at all? And secondly, we want to discuss a particular approach to quantum gravity, namely loop quantum gravity. And my lecture will focus even on a specific area in loop quantum gravity, namely the canonical formulation. And in order to be able to tell you how we quantize the Einstein equations or general relativity with canonical quantization, we have to formulate general relativity in a Hamiltonian language. And in loop quantum gravity, we do this by using a specific choice of variables, which are the so-called Azteca-Barbero variables, which I will introduce during the lecture. Once we have decided what kind of classical starting point we take, we will apply a standard canonical quantization to general relativity. And since general relativity is a system which includes constraints, and we will discuss in detail in the lecture what I mean by that, it's a bit more complicated than the quantization you are familiar with from your quantum mechanics lecture. And therefore, we will also discuss the so-called relational formalism, which allows us to quantize systems with constraints in a certain way. Then the final 2 lectures will discuss the kinematics. So how do we get the corresponding Hilbert space? How do we get the elementary operators? And finally, as physicists, we are usually not interested only in kinematics, but we also would like to evolve and predict things. And therefore, the final lecture tomorrow should cover the dynamics in canonical loop quantum gravity. So let me say a few words on the motivation. So if you are familiar with theoretical physics, you know there are 2 lectures you might have even listened to in your PhD course or in your studies, which are particle physics, which is described using the standard model of particle physics, where we apply or where we use a quantum field theory, which is formulated on a flat spacetime, so on a Minkowski spacetime. In this setup, the spacetime is fixed and you just quantize matter. Yeah, so that's how the standard model is formulated. And in particular, it's a background dependent theory because the metric is non-dynamical here. And often when you go to your your standard model lectures, you see that if we make predictions on interactions of elementary particles, we do this using perturbation theory. Now, on the other hand, there is general relativity, which allows us, for instance, to apply it to cosmology and learn something about our universe. And there, the metric, on the other hand, is a dynamical quantity. So it's evolving and it's interacting with the matter that sources the geometry. In contrast to the standard model, it's a classical theory. So in this sense, the 2 columns we have in theoretical physics are quite different. But both of them are not completely satisfactory in the sense that if we apply them, there are some limits of these models or theories. So for instance, in the standard model, you might know if you really compute scattering amplitudes, often you get infinities and you have to apply renormalization techniques to get rid of them. Secondly, if we look for solutions of Einstein's equations like black holes or cosmology, we know that in the classical theory, we have singularities like the Big Bang singularity or the singularity in the interior of a black hole. which always indicates if this happens that your model is not complete and you have to go beyond the already existing models. And that's the idea what quantum gravity would like to do. Yeah, so if we consider the right-hand side and write down the classical Einstein equations, here on the left-hand side, you have something which describes the geometry, which we will discuss more in detail during the lecture. And on the left-hand side and the right-hand side, you have matter, and they are coupled in a nonlinear manner. Now, as you know from quantum mechanics, if we canonical quantize, usually we take a classical system as a starting point, which would be GR here. And then we apply a procedure to promote the classical quantities to operators. So one aim of loop quantum gravity in the canonical approach is to really lift this to the level of the quantum theory and write down the so-called quantum Einstein equations, where all these geometric quantities like the Ricci tensor and the Ricci scalar and the metric become operators. And similarly, we know from the standard model how to quantize the matter on the right-hand side. Now, given this is in a sense a mathematical procedure, but then of course we are interested in what are the consequences. We know already from quantum mechanics, if we promote classical systems to the quantum level, there are new effects. And you can ask the same if you quantize general relativity. Yeah, so for instance, a question would be, what new effects do we get if we take quantum cosmology instead of classical cosmology? And interestingly, and you will hear this also during the lecture and during the upcoming conference, especially as far as these singularities are concerned, we get new effects or new results, such as, for instance, that these are resolved in simple models. Similar question you can ask for black holes. What are the properties of a quantum black hole compared to classical black holes? You can even go beyond this and ask, maybe quantum gravity can explain what space-time is at all and that it emerges from some underlying more fundamental theory. And all these questions will be discussed during the school and during the conference next week. Okay, now let me go to my second part, which covers the formulation of general relativity in terms of Ashtika-Barbero variables. That's our final aim. And I structured it in 4 individual parts. First, we discuss a little bit how we formulate constraints, Hamiltonian formulations of systems which include constraints. This is important because general relativity is particular one of these examples where we have to apply this. And if we have understood a little bit what these constraints are and how do we deal with them, I will briefly discuss their classification because we distinguish 2 types of constraints, and that's also important later when you quantize. Now, the original first Hamiltonian formulation in GR was given by in ADM variables, and this I will also briefly cover. And this is then the starting point to explain what these Ashtika-Barbero variables are and how they are related to the ADM formalism. Okay, so let me start with describing what we do roughly in classical mechanics. So you have an action, which is a functional of the configuration variables here denoted by Q, and you integrate over the temporal coordinates and just consider the Lagrangian here, which depends on Q, the velocities and the time, and that's basically covering your dynamical system. Now, let me just say that F is the dimension of our configuration space, and I use shorthand notation for all these components the velocity and the configuration variables have. Now, when we go to the Hamiltonian formulation in classical mechanics, we basically want to describe everything in phase space, so in terms of not configuration variables and velocities, but configuration variables and momenta. And for this purpose, we perform a so-called Legendre transformation, and we introduce for each configuration variable canonical momenta, which we get by just differentiating the Lagrangian with respect to the involved velocities. Now, if you consider the Lagrangian, and in standard models, the standard kinetic term is usually quadratic in the velocities. you can take the second derivative of the Lagrangian with respect to the individual velocities, take this as a matrix and consider its determinant. This will be the Hessian matrix of the Lagrangian. And you can test whether this is non-zero or vanishing. And if this is non-zero, you are able, by performing the Legendre transformation, to solve the relation of the canonical momenta, which we have here, for the velocities. If the determinant is vanishing, this is not possible for all involved velocities, and this indicates that we will have constraints in this system. So we would call a Lagrangian where this is satisfied regular and where this is vanishing singular. And just take a very little example here from classical mechanics of this Lagrangian, which has a standard kinetic term here in x, then a mixed term of x and y, and some potential term here. You see that there is no y dot involved, so no velocity with respect to y. And this already means that if we compute the canonical momenta for y in this case, that this will vanish and we cannot solve for the y velocity, obviously. So what do we do if we run in such a situation? So where we have a vanishing determinant of the Hessian of the Lagrangian function, we can basically look at the rank of this matrix, and let's just assume that this is F minus R here, where R is smaller than our dimension of the configuration space. Now, if this is the case, we can still solve for a subset of velocities, which I indicated with capital J here. So we build all canonical momenta, solve for the velocities where this is possible, Q dot J, and J runs then here from 1 to F minus R. So it's not possible for all R velocities. And I call this function of the velocities G of J, which will be a function of the phase space variables, and in particular, in general, also the Pj, which we can construct. Now for the remaining momenta, which I labeled by A here, this is not possible, and we will just get in general a phase space function here, which I called HA here in the second line. And we will just use this relation that PA is minus HA and take this as a so-called primary constraint of our system. And this happens always when you have a singular Lagrangian. So what do we do then? Because we still want a Hamiltonian formulation. And the idea is that you perform the Legendre transformation for all variables where it's possible, for those where you could solve the velocities and express them in terms of the momenta. And for the remaining velocities, which I call VA here, you just keep them as Lagrange multipliers. Now, if you do this, you can perform the Legendre transformation, and you can always write the resulting so-called primary Hamiltonian in a form where you have a term which I called H naught here, which includes Qj and the Pj momenta for which we could solve, plus a term which include the VA Lagrange multipliers contracted with the primary constraints. So that's the standard form we get. And if we look at our example, this indeed works. Taking this Lagrangian, we get the momenta. We have one primary constraint here, which means that Py is vanishing. And then if we construct the primary Hamiltonian in the way I just discussed, you really see it can be written as sum H naught, shown here, plus V1 times phi1 in this case. Now you can also check this yourself later because the notes will be provided. This works also in the general case. And doing that, we have the equation of motions in a constrained system, which is basically given by the standard Hamiltonian equations here for Q and P. And in addition, because these variables are not all independently, because we have constraints, we also have to require that these primary constraints vanish. And this is equivalent to taking the derivative of the primary Hamiltonian with respect to the Lagrange multipliers. This is the set of dynamical equations that we usually have to deal with in constrained systems, and it will also be the case for general relativity. Okay, what happens if these primary constraints are there? It means that our phase space is not the entire phase space, at least the physical sector is not the entire phase space, but the constraints restrict in the phase space to a certain so-called constraint hypersurface. And this I indicate by taking the phase space restricted to the constraint hypersurfaces hypersurface phi equal to 0, which means that all the primary constraints need to vanish. Now, if we think about evolution, and let's say we ensure that the primary constraints are satisfied at one instant of time, of course, it's dynamically only consistent if this is also ensured and preserved under the evolution. And therefore, we require that if we consider the dynamics with respect to the primary Hamiltonian of the primary constraints, which we just get by taking the Poisson bracket between the primary constraints and the primary Hamiltonian, which explicitly is written here. It's a contribution from H naught and a contribution of the Poisson brackets between the different primary constraints. You want this to vanish in order to ensure that the constraints are preserved at any time. And this gives a condition on the primary constraints, on their stability, and there can basically occur three different cases. If you check this condition, it could be that this is identically satisfied, and satisfied means weakly, and weakly means it should vanish up to constraints which are already in your system. Yeah, so if this equation can be written as some combination of already existing primary constraints, we would say it's satisfied. The second case is that this is not satisfied, so it's non-vanishing on the constraint hypersurface. But in addition, the Poisson bracket between these different primary constraints is vanishing weakly. So this might be for a certain subset of your primary constraints given, and I just called this subset it runs from A, where alpha plus 1 I runs from alpha plus 1 to beta. So let's say alpha of the primary constraints satisfy already case 1, then beta of them satisfy case 2, and there might be some left which don't satisfy case 1 and case 2. Which means they also are not stable under the dynamics. But in contrast to case 2, you can compute the matrix of these second-class constraints, and it has maximal rank. So these are the three cases that can occur. And each case tells us basically how we perform in that situation. So for case 1, they were already stable, so nothing needs to be done. It's a consistent primary constraint. For case 2, we get something which is non-vanishing on the constraint hypersurface. So we have an additional constraint that we have to add to the system, and this needs to be done for each constraint which shows up in case 2. Now in case 3, we also have no preserved primary constraint, but since the rank is maximal here, as you can see in the condition of the stability, you have the Lagrange multipliers, VB here. Now, if we have maximal rank in case 3, we can basically set this equation equal to 0 and solve for the involved Lagrange multipliers. So in this sense, case 3, here you fix a certain subset of the Lagrange multipliers in order to ensure the stability of those primary constraints. So which means if you have checked which cases your primary constraints belong to, you are done in case 1. You get additional constraints that you have to add to your system in case 2, and you fix a certain subset of Lagrange multipliers in case 3. Now, for those additional constraints, you also want to have them stable under the dynamics. And therefore, you have to run the whole algorithm again and see whether the stability of your additional so-called secondary constraints are case 1, case 2, or case 3. Now you run this algorithm until no longer case 2 occurs, so no additional constraints show up. And by this, basically, you get your final set of constraints. Now, if you perform the stability analysis, it's important to remark that the primary Hamiltonian only includes the primary constraints, even if you add, if secondary constraints show up. However, the constraint surface, which finally defines the physical sector of your model, is defined by considering all constraints, including those secondary constraints which show up in the analysis. Now, let's just go back to our example, to the simple Lagrangian. We already saw we have one primary constraint, which was that Py is vanishing here. We have to consider its stability with respect to the primary Hamiltonian, which has this simple form in this simple model. And we just consider the Poisson bracket of her primary with phi 1. And we realize this is non-vanishing. We basically get this right-hand side here of phi 2. It's non-vanishing on the constraint hypersurface, so we get a secondary constraint. Now we have to test whether this phi 2 is stable with respect to the dynamics of the primary Hamiltonian. And we see this basically brings us into case 3. And in case 3, we could use that we can solve the stability condition for the Lagrange multiplier, which is just V1 here in this simple example. So we are in case 3, and we just ensure stability of phi 2 by choosing V1 of this form. And then you have a consistent dynamical system with 2 final constraints in your final set of constraints. Okay, before I continue and tell you something about the classification of these constraints, are there any questions so far? I see one in the back and one in the front.
Yeah, so my question is related to case 2. So when we get additional constraints and they correspond to case 2, and then we have to check their stability, do we take their Poisson brackets for the primary Hamiltonian or the primary Hamiltonian plus the new constraints that we get?
No, it's only the primary Hamiltonian in this case. This was my first remark here.
Okay, oh, thank you.
There was another question here and one here, I think.
You said that the constraint, like the primary Hamiltonian, picked out a hypersurface. I kind of want to ask a bit more specificity on the specific term used, hypersurface. Did you mean like an integrable hypersurface or something more along the lines of a distribution or a submanifold or a subbundle? Like what more specifically does it pick out?
So it really depends on the form of the constraints, and it can be a very complicated object, much more complicated than the original kinematical phase space. So this really depends on your system, and you have to see this from case to case.
Thank you.
There's one more in the back.
So I have a question like in this example, for instance, we have this secondary constraint, and why didn't we add another multiplier, Lagrange multiplier for the secondary Hamiltonian constraint?
So this is in a sense the same question that was asked here. I will come to this back later. So when we classify between first and second class constraints, what you do in the end, you can extend the primary Hamiltonian by additional Lagrange multipliers, which include all first class constraints. And that's probably that you are referring to. And this goes back to the fact that we finally are interested in objects which commute with first class constraints. And then the dynamics is independent of these first class Lagrange multipliers. But I will come back to this in the more general case.
I wanted to ask, so we have a constraint constraint surface when the Poisson bracket of the constraint vanishes with the primary Hamiltonian. You also said that we also have to check if the Poisson bracket of the constraint with other constraints is also 0. Is there a geometrical picture that goes with that?
Yeah, maybe it's also easier to answer once we have done the classification, because this relates for second class constraints to a new Poisson bracket, the so-called Dirac bracket.
Right.
Here it was really in a sense, a technical assumption, because either I have a system involving a finite set of Lagrange multipliers, which I can solve for them if the rank is maximal, or I can't.
Right. I just have one more question. That say we check for a constraint and it and it's the Poisson bracket where the primary Hamiltonian vanishes. Do we also check its Poisson bracket with other constraints? Right. Thanks.
We have another question right there.
My question is, Lagrange multipliers are more general than just the velocities, right?
I didn't hear, did you say more general than just the master constraint, or?
Than just the velocities, because I'm getting the idea that we're interpreting the Lagrange multipliers here as velocities, some velocities.
Yes.
But they are more general. They're not always just the velocities, right? Or am I?
Yeah, so this goes a little bit back to the way how we construct the primary Hamiltonian. If you perform these this Legendre transformation, you see you couple the momenta which cause the constraints to these Lagrange multipliers. So if you perform the Legendre transformation explicitly, you can basically see that these velocities, which we couldn't solve for, are related to these Lagrange multipliers. This is generally the case.
Ah, okay, okay.
I think that's all.
Okay, thank you. Then let me continue. Let me just check where we were here. Okay, so now we have our final set of constraints, and we would like to classify them. And the classification is done by two kinds of constraints, among which we distinguish. And this will also yield us to the notion of the Dirac bracket, which becomes important in the case of second-class constraints. And the first type of constraints that we call first class. And those constraints have the property, if we consider their Poisson bracket, let's say here constraints, we have a given set, our final set of constraints phi, and I is just some index set. Yeah, it just labels the final number of constraints you have, primary, secondary, and any one which comes up later in the algorithm. And now we can check whether the Poisson bracket of these two for generic I and j can be written again in terms of a linear combination of constraints. And the coefficients are here some structure constants f, I, j, k. If this is the case, let's say for a subset of our final set of constraints, we call those subset first class. Which also means if this is given, because we have constraints on the right-hand side, if we consider the weak equality on the constraint hypersurface, these are abelian. Now, if this is not the case, we have constraints where this might not be satisfied. We call those constraints second class. Also, just to remark, when you compute with those constraints and the formalism, of course, if you compute Poisson brackets, you do this first and then apply the weak equality. Otherwise, you just get trivial zero everywhere. So in our example, when we go back to our Lagrangian, we have these two constraints, primary and secondary. We can compute their Poisson bracket, and we see it's equal to 2, which is definitely non-vanishing on the constraint hypersurface. So from the classification, we would just follow these are second-class constraints. Now, the generic situation is that let's take our final set of constraints. A subset of them might be first class, which I label by A1 here, which runs from n to from 1 to n1. And you have another subset of constraints, which is second class. I label the first one with a bracket 1 here, the other one with a bracket 2. And of course, the sum of A1 and B2 needs to be the final number of constraints, so capital N. Now, the question is, if we have a certain subset of second-class constraints, which we have satisfied, are we sure that this subset is irreducible? And by this, I mean, it could be the case that if you use certain combinations of second-class constraints, they become first-class. And in this kind of separation into first and second class, I assume I have checked this already. And really, phi 1 is the set of first class and phi 2 the set of irreducible second class constraints. So how can I check whether a set of second class is irreducible? So what I can do is I can define a matrix which is labeled by A2 and B2, so the index of the second class constraint. And the elements of this matrix are all results of all Poisson brackets of the second class constraints. If I do this, I can check whether the determinant is vanishing. If this is the case, I know that VA2 contracted with this Poisson bracket is weakly vanishing, which means there's a non-trivial solution for the V here, which means there exist additional combinations of second class constraints which are first class. And therefore, we just define these matrix. If the determinant is vanishing, it's non-invertible. If it's non-vanishing, it's invertible. And if this is the case, then we say we have an irreducible set of second class constraint. Now, why do we distinguish between first and second class constraints at all? When we later construct observables, which are in the case of GR, things which are invariant under gauge transformations or gauge we consider in GR, and this also would work, for instance, for the standard model, then we are looking for functions on our phase space which have the property that they commute with all first-class constraints at least weakly. Yeah, so for instance, a first-class constraint would satisfy this condition. But in general, we look for different things than first-class constraints if we think about first-class functions. So this is a more general notion here. Now, given two first-class functions, we can compute their Poisson bracket, and we can ask, is this again a first-class function? So is this in a sense closed? And yes, this can be easily shown by using the first-class property of your function, and the constraints and the Jacobi identity here. So this is a little problem you can do yourself. It's not hard to show that. Now, given this classification, let's go back to the primary Hamiltonian and see how it looks like. So let's again assume we have a final set of constraints phi I here. We separate this into primary and all the remaining constraints which come up in the Dirac algorithm at the second, third, fourth, or any other finite step. So phi I is the primary, chi I are the remaining ones. Now, doing this, we know the primary Hamiltonian is H naught, Lagrange multipliers contracted with all primary constraints. And now I would like to split those primary constraints into first class, which have on the top these label 1 here, and second class constraints. And I also labeled the Lagrange multipliers accordingly. So the first class one have V1, the second class one have V2. So now let's consider their dynamical stability. We know we have to check this for all primary and secondary constraints. And if I have this split now in terms of phi I and chi I and into first and second class constraints, the stability condition that the dynamics of all constraints need to be stable under the evolution of the primary constraints splits into these two parts. So for first class constraints, since they commute with all other constraints, the Lagrange multipliers are absent in the stability condition. For second class constraints, you still see they are involved. And what enters in the stability condition is, of course, also the Poisson bracket with H naught. And then some combinations here of secondary and primary constraints in general. Now, we know that in this first condition, we will not fix any Lagrange multipliers. This is a property of first class constraints. So if you have them in your system, they will just be arbitrary even in the final primary Hamiltonian. Now, this condition 2, we can solve for the Lagrange multipliers if we have a set of irreducible second class constraints, because then we can basically consider the matrix here, which I called M, I tiddle, J tiddle, which now includes all Poisson brackets of all possible second-class constraints, independently whether they're primary or secondary. Yeah, so this is this phi 2 with a twiddle index in order to distinguish the index we had before. Now this has an inverse, and you can use that to solve for the Lagrange multipliers, which are here in the stability condition, which will fix them in a similar manner as we did in our very simple example where V1 was fixed, and plug them in back into the primary Hamiltonian. And then the evolution equation for a given phase-space function f has this form. It has a contribution coming from H naught. Then you have the first-class primary constraints here with generic Lagrange multipliers. And this additional contribution here, which involves the inverse of the second-class matrix here, is basically the result of fixing these Lagrange multipliers here on the top. And this has a specific structure, namely, we can combine all these terms here into one bracket, a new bracket, which has a star here, which is the so-called Dirac bracket, which I have displayed here below. So the Dirac bracket of two phase-space functions is the original Poisson bracket that we have here. And then you get an additional term, which involves these two functions f of f and g, the inverse matrix of the second-class constraints here. And here in the bracket, these second-class constraints contracted with the inverse matrix, which shows that second-class constraints have always the property that we fix some Lagrange multipliers, so they are not arbitrary anymore. And you can rewrite the dynamics if you have second-class constraints in terms of this new bracket, which is this so-called Dirac bracket in a very compact form. As we will see on the way, when we have second-class constraints and we think about quantization, usually as a first step, we have to go to this Dirac bracket instead of the Poisson bracket. And what you see is that it's the Poisson bracket plus, in general, non-vanishing contributions, which means that if second-class constraints are in your system, it's also not unlikely that the algebra that you later have to quantize is changing, and in general might be more complicated. Good. If we do this now, we can basically consider the Dirac bracket, which is in our system, and similar to the Poisson bracket, it satisfies the Leibniz rule, it's antisymmetric, and it also satisfies the Jacobi identity. So apart from maybe being a bit more complicated, it has quite similar features. And doing this now, we can rewrite the primary Hamiltonian in this form. And now I will basically come back to the question that was asked before. So now if we have a first-class function, we know it will commute with all first-class constraints, which means with all constraints which have a label 1. And as far as we discussed, the primary Hamiltonian only included the primary first-class constraints. However, since any first-class function will commute with any first-class constraint, independently whether it's a primary or secondary, what one usually does is one considers the set of all first-class constraints, adds additional Lagrange multipliers for those which are secondary first-class constraints, and then writes the Hamiltonian in this form, so that it's no longer the primary Hamiltonian, but in addition, we added any secondary first-class constraint which showed up in the Dirac algorithm. Now, taking this set of first-class constraints and going back to the original interpretation Dirac had when he was developing this formalism, he would say that all these first-class constraints are the generators of gauge transformations. We will see this in general relativity, and where we have explicit examples for the set of first-class constraints. But you can also see this, for instance, in other gauge theories that you use in the standard model. And in this way, by applying this Dirac algorithm, which you anyway need to do in order to perform the Legendre transformation, you also get the final set of first-class constraints and also know what are the gauge symmetries in your system. Okay, now since we distinguish between weak and strong equalities, so equalities which are satisfied only on the constraint hypersurface, let me now introduce as the last notion in this chapter the so-called Dirac observable, which is a quantity which commutes with all first-class constraints, at least weakly, so up to constraints. And going back to the interpretation, this would be the quantities which are gauge invariant in this setup. And these are usually the quantities that we are interested in if we work with constraint systems. If this is an equality which is satisfied on the entire phase space, so I don't have to, not only on the constraint hypersurface, then we would call such a quantity a strong Dirac observable. And as we will see on the way, these objects are important if we apply a certain type of quantization when constraints are in our system. Okay, so I would again ask whether there are questions to this part, and otherwise move on to the Hamiltonian formulation of general relativity. Okay, seems not to be the case. Now then, let's apply all this to the theory that we are interested in, which is general relativity. And for this, we first need to bring general relativity into its Hamiltonian formulation. And for this, I will explain and discuss how we can apply this Dirac algorithm I was just explaining. And this I will do in the standard canonical variables, the so-called ADM variables. And afterwards, once this is done, I will explain you how we can go from these ADM variables to Ashtekar-Barbero variables. Okay, and as before in classical mechanics, the starting point is some action. Here we take the Einstein-Hilbert action, which is a functional of the metric. We integrate over some manifold n. We have a coupling constant 1 over kappa, which I took to be 16 pgn. We have the Ricci scalar, and we have the determinant of our metric. So I assume space-time is 4-dimensional, so the coordinates here are x mu, and mu runs from 0 to 3. Now we would like to introduce a notion of time in order to define canonical momenta. And for this, we have to restrict to globally hyperbolic manifolds, which can be written as R cross sigma, where sigma is a 3-dimensional manifold. Now on this 3-dimensional manifold, I also introduce coordinates, which I call lowercase xa, and a runs from 1 to 3 here. So what we do is we slice our 4-dimensional spacetime M here, curly M, into 3-dimensional hypersurfaces, which are embedded in M, which I call sigma 1, sigma 2, sigma 3. There is an embedding map which embeds sigma for each value of t into M, which I call xt1 of sigma here, for instance. Now the time evolution is along a time-like vector field, which I call T mu here. And we can split those vector field into its normal and tangential direction. Yeah, so the normal to, let's say, the sigma 1 hypersurface here is n mu. And then you split T mu into its normal and tangential direction. And this we parameterize here in terms of a so-called Labs function, which I call n. Which is shown here, and a so-called shift vector n mu, which has the property that if I contract it with the co-normal, this vanishes. So it's really indicating the tangential part. And this can be obtained from the embedding map x mu t by taking its derivative, partial derivative with respect to t. So n mu is equal to -1 if I contract the co-normal and the normal. So given this, we can basically consider the time evolution along T mu, and you see that this is parameterized by choosing lapse and shift, which means that if we would fix lapse and shift, the slicing would be determined by it. And since we would like to consider this for any slicing, we keep n, so the lapse function and the shift factor generic. Now, how do we get these final Hamiltonian formulations? So the idea is to rewrite the Einstein-Hilbert action here. So I restrict to the vacuum case here for simplicity, but in principle, you can do this also if you add matter. If we take this, we want to write this four-dimensional integral in terms of an integral over this t parameter over R and an integral over our three-dimensional manifold sigma. And in order to do this, we need to be able to express all these quantities contained in the Einstein-Hilbert action in terms of quantities which are related to tensors on the spatial hypersurface, on the spatial manifold sigma. And for this, we have basically also to split our quantities like the metric into its tangential and normal part. And one does this by introducing the so-called two fundamental forms. So the first fundamental form is the spatial projection of the four-dimensional metric G, which is given by G plus the conormals NU and NU. If you contract this with a normal vector, we know its norm is -1. So basically, you see that it's vanishing. So it's a spatial tensor. And we can use the embedding map in order to pull the spatial projection of G to sigma, just in this form. And then we have the so-called ADM metric, which now has indices related to the labeling that we were using for the sigma manifold. So this is QAB. And this is what people call the ADM3 metric. Now, the second fundamental form, the extrinsic curvature, is related to the way how the normal vector changes along the hypersurface. And you can express this in terms of the covariant derivative of the conormal. And then you have contraction here with the spatial metric. And if we consider this, we can rewrite this in terms of the Lie derivative along the normal of our spatial metric up to a factor. And since we have this split into tangential and normal parts, we can use this in this expression here and rewrite the extrinsic curvature in terms of a Lie derivative along T minus a Lie derivative along the shift vector of the spatial projected metric. And this three-dimensional vector on sigma we get by using, again, the embedding function. So this is only the metric. But to re-express Einstein-Hilbert in terms of these curvature quantities, we need also to be able to express the four curvature, which is included in the Einstein-Hilbert action, in terms of the Ricci scalar on sigma, so which gets a label 3 here. And since this information in the four-dimensional curvature scalar is more than in the three-dimensional, we get additional terms. And there is a so-called Gauss equation, which does exactly what we want. It relates the four-dimensional Riemann tensor here on the right to the three-dimensional Riemann tensor. And the additional terms that we get here are related to the extrinsic curvature. Now, given this relation among the Riemann tensors, we can construct the Ricci tensor and then the Ricci scalar. And there's the Kodacci equation, which tells you also a relation among the four-dimensional Ricci scalar, which is included in the Einstein-Hilbert action, and the three-dimensional one, where you get, again, contributions coming from the extrinsic curvature, where k square here is just the trace, plus some term which, if we neglect boundary terms, will drop in the action, which includes, again, the normals and its covariant derivatives. Given that, we have more or less everything available in order to write the integral of the Einstein-Hilbert action adapted to our slicing. And in order to finally do this, we also want to express the metric in terms of t and xa coordinates. And if we do this by just considering the line element g mu nu, dx mu, dx nu, and then use that dx mu can be written in this form, so partial derivative of x mu dt plus spatial derivative of x mu dxa, we can express our four-dimensional metric entirely in terms of the ADM variables, which are the three metric, the shift vector, and the lapse function. And the metric has this form. So in the spatial coordinates, you basically have the ADM metric, and in the 0a coordinates, you have the lapse function and the shift vector, and yeah, some combinations thereof. The inverse metric looks in this form, and as expected, can also be entirely expressed in terms of these ADM variables. Which means that we managed to rewrite these four-dimensional metric in the quantities that we are interested in. And now we can basically write the action in the ADM form and express it as an integral over R over dt, an integral over sigma. And the Einstein-Hilbert action includes now the three-dimensional Ricci scalar, some additional contribution from the extrinsic curvature, and the determinant which is involved there can be written in terms of the lapse function times the square root of the determinant of the ADM metric. So let me just finish here by saying that because we want to continue in the next lecture and perform the Legendre transformation, so where are the velocities? And the velocities of the metric are encoded in the extrinsic curvature here. So you see here is a derivative with respect to t of QAB. And that will be then used in the next lecture in order to derive the canonical momenta. So I will stop here because it's exactly 10 o'clock, and I will just ask John to close that session, right?